Okay, this is going to continue our section 1. We're actually going to look at those initial condition problems so we can fill in that value of C, our constant of integration. So the general solution gives you every possible function that could give you your f of x, your little f of x as a derivative. So if we know one value of that function that we're integrating to find, we can find the particular function that corresponds to it. So here's an example of how we'll be doing this. We're going to solve the differential equation, and we're going to use the initial condition to fill in that constant of integration. So let's see, we've got f prime of x is this. All right, now this is a product, and we don't really have a product rule yet for integration. So what we're going to want to do is we're going to want to simplify this so we can have just individual terms that we can integrate. So I'm going to distribute this t squared inside. So really my derivative can be rewritten as t squared plus 3t to the third. Okay, and I want to integrate both sides of this. And this is dt. And this should also be a t here. Okay, so now when I integrate, I can give each of these terms their own integral and their own dt. And so f of t, okay, this is power rule, so I'm going to raise the power by 1. Take it over that same power. I'm going to raise the power by 1, so I'm going to have a 3, t raised up by 1 power, and taken over the same power. And then I've got this big plus c. Well, if I know that the actual function, so I guess I don't really need this capital F here, since they gave us f prime. Okay, I know the function, when x is 1, I get out a value of 4. Well, that means if I plug 1 into this, okay, so if I plug 1 in right now, I'm going to get 1/3 plus 3/4 plus something has to equal 4, because that's what my function's value is at 1. So I need to find out what constant is going to give me 4. So let's get a common denominator here. So this would be 4/12 plus 9/12 plus c. So we've got 13/12 plus c has to equal 4. Well, 4 is really 48/12. If I have 13/12, I need 48/12. That means I'm missing 35/12. That's what c is. Okay, and you can get that just by subtracting also. Whoops, 12ths. Okay, so my actual differential equation solution with this initial condition is that f of t equals my integral, so t cubed over 3, which we could also write as 1/3 t cubed plus 3/4 t to the 4th plus 35/12. And this is the specific function that would give me this derivative and meet this initial condition. Let's look at a physics problem. A ball is thrown upward with an initial velocity of 80 meters per second and its initial height of 30 meters. Find the equation for the height as a function of time and when does the ball hit the ground. So if you remember the function for vertical motion, okay, we need to take, we're in meters per second, so we need the gravitational constant. Okay, so if you remember, this is usually -1/2 the gravitational constant times the time squared plus the initial velocity times the time plus the initial position. So when we're all done, we should get something in that kind of a form. we're going to take what they gave us and kind of come back to that as our answer. I know that the initial velocity, so the velocity at time 0 equals 80 meters per second. Okay, velocity is really the first derivative. So I know that the first derivative at 0 has a value of 80. I know that the actual position function at 0 has a value of 30, because that's our initial height. And I know that our acceleration, okay, which would be our second derivative at 0, or actually at every time, okay, our second derivative is always going to be the negative 9.8, because we're in meters, so we want to use the meter. Well, if I start by integrating my second derivative, okay, so I'm going to integrate this to get up to my first derivative. So when I integrate, I'm going to get, this is a constant, so when I integrate a constant, I just get this. This is now my plus c. So my first derivative would equal this. I'm going to use my initial condition for my first derivative. So if I put 0 in here, I know I should get 80 out. So if I put 0 in, I'm getting 0. I mean, c is going to have to be 80. So my real first derivative function is negative 9.8t plus 80. If I integrate again, okay, and I'm actually going to split my integral up, okay, that should bring me to my position function. So here I've got a power rule now, so I need to raise my power up by 1. So I've got my constant, my t raised up, also divided by that same power. This integrates to just be 80t, and then I've got my constant again. If we simplify a little bit here, this is negative 4.9 t squared plus 80t plus some constant. Okay, this is my position function. I need to find out what that c value is, so I'm going to use my initial condition for that. When I plug 0 in here, I need to get 30 out. Okay, 0 make both these terms 0, so c is going to have to be 30. And this is the equation that meets my initial conditions. Okay, it has an initial velocity of 80. Okay, if we compare it to what we should have, negative 1/2 gravity, which is what I have, t squared plus the initial velocity 80 plus initial position 30. Okay, so that's how you can use initial conditions to get specific equations that meet initial conditions. The other part of this is slope fields and some graphs. So slope fields, we haven't done these before, but basically this is a slope field. Okay, and I put this point in for a certain reason, but this is the slope field of this function. So these little blue lines actually represent the slope at certain x values. Okay, so if I look at 0, everywhere where x is 0 has this slope. Okay, so if I want to trace a certain function that is in this slope field, I'm basically just going to follow the slopes as I move from left to right. So one possibility for a function, okay, I can see that I'm starting pretty steep here. So we got this steepness. Okay, we got this steepness. Starting to get a little less steep. Okay, and then I'm starting to go down. So I'm just kind of following these slopes as they go. Here it kind of flattens out, and then it starts going up and gets steeper and steeper and steeper. Okay, so that's one way we can trace through here. If I want a specific, so let's say I want the function that is in this slope field. Okay, so this would actually be an f of x, not an f prime of x. If I want the one that goes through this specific point, then I'm just going to trace and make sure I go through this point. Okay, so I've got these slopes, steeper, steeper. I guess I shouldn't quite be vertical there, but steeper and steeper. Okay, and then I just keep following these slopes. Okay, and that's kind of an initial condition slope field problem. So not too bad. You're basically just looking at what the slopes are at different spots. Also, if they graph a derivative for us, and maybe they're asking us some questions, so maybe they want us to draw the function based on the derivative function, things like that. I just want you to remember that certain things you can get from the derivative function. So when the derivative function is 0, which I don't have any zeros here, that would be a min or max on your actual function. So since I'm not crossing 0 anywhere here, that means I don't have any mins or maxes on my function. So I shouldn't have any hills or valleys, okay? Peaks or troughs. I shouldn't have any of those on my function when I go to draw it. Remember that this also represents the slope. So this is positive. Okay, my numbers are all positive. They're always positive. So I should only have positive slopes. Okay, and actually, this is a low positive number. And then slowly goes up to a higher positive number. So a low positive number is kind of a low sloping line. So if there's a low sloping line, and then it's getting steeper and steeper and steeper. Okay, until I have something like that. Okay, so this has a slope value of 9, which means right at this point, you know, if I drew a tangent line here that has a slope of 9, so let's see. So if I go down 1, 2, 3, 4, 5, 6, 7, 8, 9, and back 1, okay, and do the same thing going the other way. 1, 2, 3, 4, 5, 6, 7, 8, 9, and over 1. Okay, this tangent line should meet my line at that point pretty well, and it looks like it does. Okay, so that's one way to guarantee. Here I've got a slope of about 3, okay, because my value is 3. So that means at this point I should have a tangent line that could be about 3 as a slope. So it might not be as good, but let's try it. So I want to go from this point up 1, 2, 3 over 1. And from this point I want to go down 1, 2, 3 over 1. So that one's not so good. My tangent line's a little off. Okay. I can see that my derivative function's undefined here, so that could be a critical point. But it's also not it doesn't exist there, so it's not differentiable there. So that means it's either a point or it's just a vertical asymptote. On the other side of my graph, this is always positive also, but this one's starting off steep and ending a little more shallow. So I could have something really steep, starting to get less positive, which means it's not as steep, and then less and less. Kind of levels off there. So in this one, the actual function ends up kind of mirroring the derivative function. Okay, so this would be the actual function. You're going to have some other examples that will have some intercepts. Okay, maybe it'll cross 0. Just remember that that's got to, if it crosses 0 here on your derivative, you have to have a min or max on your function. Now, I could have drawn the same function, okay, and I could have shifted it anywhere because it's not giving me any actual positions. It's just giving me slopes. So as long as I meet those slopes, I could position it anywhere. Maybe I can even have one that's up here and one that's down here. Okay, I don't have any information that's going to tell me where the position actually is, or where the function actually is. And this kind of relates to our slope fields too, because I could have this function, you know, anywhere on this slope field. It's only if I have an initial condition that I can get the actual position of it. So that concludes all of section 1. You should be able to do the second part of that assignment now.